Hello there. Now, I know you're all double integral fans out there. I can just hear you cheering right now. So I'm going to do a little bit of work with a double integral. It's not that bad as long as I'm sticking to rectangular regions. So here's a joint distribution of a variable, x to the minus 2, y to the minus 2, for x going from 1 to infinity and y going from 1 to infinity. Kind of depressing. It turns out these two are not that exciting because they're independent. Anytime you can factor the joint distribution into an x part and a y part, it's going to turn out that we don't have independence. But still, let's work with this. So we'll get the marginal distribution of x. Then I'll compute from that marginal distribution x probability of x greater than 2. Because notice, this probability only involves x, so I can work with the marginal distribution, which only talks about x. Then I'll do a joint probability, x less than 2, y less than 2. It'll involve drawing a picture and also doing an integral. So let's get the marginal distribution, shall we? This will be just so exciting I can almost not stand it. Hold on. Aha. Let me do this. So to get a marginal distribution, you want to get rid of one of the variables. We'll get rid of y by integrating over y. So we'll do our integral from, okay, we're getting rid of y, so y goes from 1 to infinity. Wow, that's snappy. x to the minus 2, y to the minus 2. Now, this is kind of a clunky way to write, I gotta tell you, the cursor. I think it's called cursor because you feel like cursing. We'll take the dy. Okay. Now, the secret to this is when you do an integral with respect to one variable, like here dy, you're going to treat x like x to negative 2 like a constant. Because of that, I can yank it right outside. In this case, because it's multiplied, I can take it completely outside. This won't always work. Sometimes you'll have to pretend it's a constant, like 2, and just work with that. But here we go. I'll go from 1 to infinity. Y to the minus 2. dy. Now, integral of y to the minus 2, I add 1 to this, and I end up with y to the minus 1 over minus 1. It's always over. This is a polynomial. And it's still going to have the x to the minus 2. There's the x to the minus 2 didn't change because I integrated over y. And then I'm going to do that from y equals 1 to infinity. Now, when I plug infinity into y, look, infinity, 1 over infinity is 0. Hey, it said Ron. I like that. It's 0. And then it's minus what I put in when I put y equals 1. So that would be x to the negative 2 over minus 1, which is minus x to the negative 2. But remember, I take plugging in infinity into it, and I subtract what I get when I plug in 1. So a minus, it's going to be, okay, 1 goes into the y. It's going to be 1 times x to the minus 2 minus a minus. And that has a range from x from 1 to infinity. And that's the marginal distribution right there. Yep. I know. Pretty exciting, huh? Okay. So, that's kind of interesting distribution. It looks kind of like this. So at 1, we get something that looks like it drops down slowly. There we go. And that's what it looks like. Okay. Now that I've done a marginal distribution, I can use that because this is only a question about x. So let's do this one. Probability x greater than 2, okay, equals I'm going to integrate this marginal distribution. Okay, the range of this is 1 to infinity, but I just want the part greater than 2. So I'm going to go 2 to infinity. And that's dx. Okay, integral of that, you add 1 to the exponent. Woohoo! Divide by that. Why does it keep saying Ron? I know my name. It must suspect something's wrong with me. The man's insane. He's doing calculus at night. Okay, 2 to infinity. Here we go. When I plug infinity into this, I get 1 over infinity, which is 0. Then I subtract minus 1 times plugging in 2 into this, so that's 1 over 2. So that ends up being 1/2, and that's the answer. So the probability for this joint distribution that x is bigger than 1/2, is bigger than 2, is equal to 1/2. Okay. Let's now do something a little fancier. I might have to add another sheet to this. Hold on here for a second. Let me see. I'll do the last one right now. Okay, here we go. Now we're going to do one over a joint region. So this is integrating over the region x less than 2 and y is less than 2. So let me show you what sort of things you have to do. All right. So let's first do a picture. Whenever we're working with a joint distribution of x and y, we should write up the support. That's where x and y are defined. X and y are defined when x goes from 0 to infinity. Well, no, it doesn't. 1 to infinity. So there's 1. Oh, uh-oh. What just happened here? Try that again. 0. Here's 1. And then here's y. 1. Okay, both x and y go from 1 to infinity, so we give this subregion up here that goes off forever. So where any values of x that go from 1 to infinity, any values of y that go from 1 to infinity. Okay. Let's see. What part of that are we going to integrate over? It's x less than 2 and y is less than 2. So let me draw that picture even bigger. Here's y. 1, 2. 1, 2. Okay. Here's the support of that function. It goes where x goes from 1 to infinity, y goes from 1 to infinity. But we only want the part where x is less than 2 and y is less than 2. Oop. Why does it keep doing that? I don't know. I don't know how to stop it. Let's see. Oh well. Draw my picture again. Here we go. 1, 2, 2. So if x is less than 2 and y is less than 2, we get this subregion right here. You know, this is really a square. It's just an extremely poorly written square. See, this is the region we want to integrate over. Because our support goes from 1 to infinity in the x direction, 1 to infinity in the y direction, but we want just x less than 2, y less than 2. So we're going to integrate over this square. As long as we're integrating over squares or rectangles, life isn't very bad. Unless you've had Calc 3 and can remember the traumatic experience that was. Okay, here we go. We write the joint distribution. no matter what it is. And this is going to be quite a workout. Okay, now we decide either to go dx or dy first. I don't have to do anything fancy with drawing lines because it's going to turn out this is a nice rectangular region. So we go dx. What does x go from? X goes, this is the x variable, so x goes from 1 to 2 in this region. And then when we do y is going to always go from 1 to 2, no matter what x is. So what we do in these things is we first do the middle central integral, dx. So let's do that. If we do this with respect to x, we treat y as a constant. So it's going to end up x to the minus 1, because that goes up by 1, over minus 1, times y minus 2, because that's your constant. And that's going to be done from 1 to 2. And that's just this middle part right here. I think it has to do with Fubini's theorem. These are all finite integrals. We could do them dx dy and we'd be okay. Plus the name Fubini is really cool, don't you think? It sounds like a food. Like I'd like a plate of Fubini. Okay, here we go. We're going to put 2 into here. We'll get 1/2 minus a half y to negative 1. Then we put, oops, I should remind us, this is equal the middle integral. That integral we've done so far is x. So when we put 2, we get a half. When we put in 1, we get 1. So we're going to get 1 y to the negative 2 minus 1 y to the negative 2 minus a half. So when we put 2 in, y to the negative 2. In case you find it mysterious, the reason they're in that direction is, look. A 2 goes here 1/2, but that's a minus 1/2. When I put 1 here, it's going to be subtracted because it's down here, so it's minus a minus 1 y squared. So this whole thing ends up being 1/2 y to negative 2. And that's for y, I'm not going to write it right here, but that's actually for y from 1 to infinity. Oh, we've only done the middle part now. Now we have to integrate that dy. So from 1 to 2, middle part is 1/2 y to negative 2 dy. And that happens to equal, okay, put on your integral caps right now. Think. What is the integral of y to negative 2? Well, this is ye old polynomial. So you'll add 1 to this and get y to negative 1 and divide by that exponent. You have a half still because, it doesn't go away. Constants just don't go away. And that's done from 1 to 2. Of course, that's y, because y is the only thing there. Look, in the first step, it's sort of like the marginal. When you take the derivative with respect to x is going to be gone, and all you'll have is y's. If you have anything but a y, you've done something wrong. Okay, now we're taking this one and integrating it with respect to y, which is the only thing there. So this is weird. It's negative. So when we put 2 here, we're going to get 1/2 times a half, a quarter. So there's going to be a minus a quarter. Put this here. And then minus a minus a, when we put 1 here, we'll get a half. So we're really going to end up with a half minus a quarter. Look, if I got it backwards, I know I will have known I did it wrong anyway, because I'll get a negative number. And this is a probability. So half minus a quarter happens to be, excitingly enough, 1/4. And that is exactly what that integral equals. I should stop now so that the excitement doesn't get too overwhelming.